Welcome back to more algebraic limits, 13.2. We have two objectives for this lesson. The first is introducing trickier algebraic cases which should stimulate your thinking about the algebra associated with limits in general. The second is looking at situations where the best way to find a standard limit is by looking at the left and right-hand limits first. So heads up. Remember, if the front door is locked, look for other ways in. Let's start by evaluating the limit as x goes to 0 of 1 over x plus 2 over x squared minus 2x. Now, it's very tempting, and you should be doing this, to first think, hey, can we evaluate this using the limit of the sum being equal to the sum of the limits? And yeah, I mean, that should be your first line of attack. That's what we've been doing. But no, that is not going to be effective in this instance. And let's look at why. If we were to plug 0 in to each of these functions, this one's undefined, and this one's also undefined. So it's not going to help us. We need to do algebraic manipulation before we can actually consider x going to 0. Let's get started with that. Now, we have a rather nice fact. I can rewrite 2 over x squared minus 2x as 2 over x times x minus 2 factors, which means we are not that far off of having a common denominator between these two rational expressions. And if you can't take the limit of f of x plus the limit of g of x, you should probably try and mush these things together and take the limit of the new object. Let's do it. We'll have the limit as x goes to 0 of, let's see, 1 over x times x minus 2, x minus 2, and we don't have to do anything to our second term. Okay, let's come back over here. Limit as x goes to 0 of x minus 2 over x times x minus 2 plus 2 over x times x minus 2. Now, when we combine these two, we are going to get a rather nice result, because x minus 2 plus 2 up top and x times x minus 2 produces first a situation where my 2's cancel out, and second, a situation where I can cancel those x's, top to bottom. So when the dust settles, we are looking at the limit as x goes to 0 of 1 over x minus 2. And that, my friends, can be evaluated. That one's just negative 1/2. Moving on, let's take a look at this sucker. Limit as x goes to 2 of x minus 2 to the negative 1 over, oh god. So again, if we think about this as the limit as x approaches 2 of f of x over g of x, and we want to rewrite that as the limit as x approaches 2 of f of x over the limit as x approaches 2 of g of x, it is completely useless. Because again, if we plug in 2 to the numerator, it's undefined. It would be 1 over 0. If we plug it into the denominator, it's also undefined. So again, we must look at another way. And in this instance, let's start by rewriting x minus 2 to the negative 1 as 1 over x minus 2. Down below, we'll still have 1 over x squared minus 4. Now, if you've got a compound fraction, if you've got a fraction over a fraction, we, from long-standing practice, know that you take your bottom fraction, you flip it, you invert it, you take the reciprocal, and multiply. And we also, from Algebra 2, should recall that x squared minus 4 factors into x plus 2, x minus 2 over 1. So from here, another nice cancellation occurs, taking us exactly where we want to be. That's going to give me the limit as x approaches 2 of just plain old x plus 2, which sure looks like 4. These next problems are absolutely different. We've already said that evaluating a limit is different than evaluating a function, but that may have gotten muddied recently. We need to highlight just how different evaluating a limit can be. And here's a prime example. Good old absolute value of x. Let's evaluate the limit as x goes to 0 of the absolute value of x. Now, we're not allowed to just plug in 0. That rule only held for polynomials and rational expressions for which the function was defined at the point you were plugging in. Now, absolute value of x is defined at 0, but absolute value of x is not a polynomial, and neither is it a rational function. We need to hearken back to the fact that the absolute value of x is actually a piecewise function. It's equal to x for x greater than or equal to 0, and it's equal to negative x for x less than 0. And that means that our best mode of evaluating this limit is to think about, first, the limit as x approaches 0 from the left, and second, the limit as x approaches 0 from the right. Now, the limit as x approaches 0 from the left will be equal to the bottom part of our function. So we can express that as the limit as x approaches 0 from the left of negative x, which is a polynomial. It can be evaluated just by plugging in, and yeah, we get out 0 as the value. The limit as x approaches from the right. Let's now move down and take a look at it. Well, limit as x approaches from the right of the absolute value of x. That means that we're living in the territory defined by the top part of our piecewise function. So that's the limit as x approaches 0 from the right of just plain old x. And that's also easy to evaluate. That's also just 0. Aha! And here we have it. Since the limit as x approaches 0 from the left of the absolute value of x equals the limit as x approaches 0 from the right of the absolute value of x, we can say that the limit as x approaches 0 in general is, in fact, equal to 0. Some people would argue that this is the most pure way of thinking about limit evaluation because it's the one that works for all the functions. It works for piecewise functions, it works for rational functions, it works for polynomial functions. It's clearly more cumbersome. We had to evaluate two limits effectively to show that that limit existed. So I wouldn't always deploy it, but it is a very solid tool. Now, let's use it to examine some of our earlier work that we previously evaluated not algebraically, but graphically, or using a table of values. So, number 4, let's use algebraic techniques this time to evaluate the limit as x goes to not infinity, that's a typo, rather 3. The limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. So this is going to be a situation where when we come in from the left, we deal with one part of a piecewise function. When we come in from the right, we would deal with another part of the piecewise function. X minus 3, if we consider it by itself, it's defined as x minus 3 for x greater than or equal to 3, and it'd be negative x plus 3 for x less than 3. Okay, so as we think about the limit as x approaches 3 from the left, we will be using this component in our expression. So rather than writing absolute value of x minus 3, if we're coming in from the left, we would write negative x plus 3 over x minus 3. Now this calls for some algebra. We're going to factor out a negative 1 up top. We'll get x minus 3. Down below we already had x minus 3. Those cancel. The limit as x approaches 3 from the left of negative 1 is simply negative 1. There's not even an x to mess with. It's just a constant, and you know the limit as x approaches anything of a constant is that constant. So there's that piece. Now, other side. Look at the limit as x approaches 3 from the right. Well, if we're doing x approaching 3 from the right, then delicate, there we go. Then that means that we are now dealing with the top piece. So this thing is going to look like x plus 3 over x minus 3. Pardon, I misspoke. Let's get that back down. X minus 3 over x minus 3. So this is the limit as x approaches 3 from the right of, well, that's a cancellation opportunity. We can cancel that all day. Let's cancel it right back here. That's just 1. Limit as x approaches 3 from the right of 1, which is 1. Okay, so then this is the operative piece here. We've got negative 1 and we've got 1. And negative 1 does not equal 1. So there we've shown algebraically that the limit as x approaches 3 of x minus 3 over x minus 3, absolute value of x minus 3 over x minus 3, does not exist. The next one's a little bit happier. You know that this limit exists. You've already done it. It's again piecewise, and it'll just be another opportunity to consider the behavior. So we'll say we're going to look at the limit as x approaches 2 of f of x, and we're going to evaluate that by doing the limit as x approaches 2 from the right of f of x, and the limit as x approaches 2 from the left of f of x. So from the right, coming in from the right, that would mean that x is bigger than 2, so that means we're working with this chunk, bigger than 2. So that's the limit as x approaches 2 from the right, oops, don't go away, of 6 minus x, which presents no difficulties with evaluation. We can plug in the 2 just fine. That gives us 4. Great. Now, for the other half, the limit as x approaches 2 from the left, that would be this piece. So we'll have the limit as x approaches 2 from the left, we're going to plug in and say that's x squared. Again, can be easily evaluated. Again, is equal to 4. Aha! So, we once more... Go away. We once more can say that the limit as x approaches 2 from the right of f of x equals the limit as x approaches 2 from the left of f of x. Thus, limit as x approaches 2 of f of x is equal to 4.